Well, then what about this opposite side? So you can think of this side as either being opposite the 30-degree angle or adjacent relative to the 60-degree angle. Well, I'm just going to think of it as opposite the 30-degree angle. And we know that sine of our angle relates the opposite side to the hypotenuse, which has length 1. So the opposite side must be sine of 30 degrees. Yeah, if you can't hear, I should have asked, but if you can't hear, maybe you want to, well, check your audio. If not, reload your tab. Okay. So this length is sine of 30 degrees. And our angle here was 60. And if you look at the overall triangle, what kind of triangle is this kind of dunce hat-shaped triangle? Well, this angle is 30 degrees. This angle is 75. So this angle must be 75 as well. As you can tell, the 60 plus the 15 gives you 75. So that's, in fact, we have two equal angles, so the sides opposite those equal angles are also equal. So it's an isosceles triangle, that is correct. Okay. So the length overall over here is also 1, just as it is on the opposite side there. So the difference between the total length of 1 and the cosine of 30 degrees, of course, is this length, which must be 1 minus cosine of 30 degrees. So if you enjoy this kind of stuff, math and engineering are definitely for you. Okay, but then there we go. Looking at our smaller triangle, the 1575 90 triangle. We now have the opposite and adjacent side relative to the angle 15 degrees. So we can write down what tangent of 15 degrees is. Opposite side divided by adjacent side. And if you know you write your unit circle, you know that cosine of 30 degrees is square root of 3 over 2. And you know that sine of 30 degrees is 1/2. So a nice exact answer without using a calculator, just an approximation. The exact answer is 2 minus square root of 3. Anyway, that was just for fun, and it took 10 minutes. Wow. Okay. So maybe the other problem I can do fairly quickly. So this is something you might see in Calculus 2, if not 1. I think Calculus 2. But this is what we call an infinite series, because you're adding infinitely many terms. So that ad infinitum just means this pattern goes on forever. And suppose that this infinite series, this infinite process of adding more and more terms goes on forever. And suppose that this process does have an end result, and that end result is a number, x. Okay. Would you be able to find that number x? Well, I did provide a hint here. If you look at the stuff that's in the green box, all the terms except the first term, which is 1. That's in the green box. Do you see a common factor in all those terms? If you imagine the pattern, well, maybe I should mention, what is the pattern in the denominators here? Yeah. So that's another thing you'll be looking at, is like, or expected to do, is find obvious patterns in numbers, in sequences of numbers. Yes, those are all powers of 2, right? So you would have 2 to the power 1, like 2 squared is 4, 2 cubed is 8, 2 to the power 4, and so on. And we all are kind of familiar with these, right? Computer science and whatnot. So do you see a common factor in all the terms that are boxed in green? All right. Well, since these are all powers of 2, they all have a factor of 2. These are all even numbers. The denominators are all even, right? So you can factor out a 2 from the denominator. If you'd like, you factor out a half. And so from the first term, after you take out a half, you'd be left with 1. From the second term, after you take out a half, you'd be left with a half. And 1 half times 1 half is a quarter. And then 1/4, 1/8, so on. And this goes on forever. Okay. So what you notice is that if x was that whole sum, you notice that you have x here as well. This whole thing is x itself, if you look at the original definition of x. X is 1 plus a half plus a quarter, and so on and so forth. So you get x is 1 plus 1/2 times, and all of this itself is another copy of x. Okay. So all that is you get 1/2 times x. And now if you solve for x, you'll find that x is a half. X is 2. Subtract half of x over, multiply both sides by 2. So that's a fun infinite game you'll be playing. Okay. So you're either turned off or motivated to learn math. So we'll see. All right. But seriously, for the agenda today is where Elliot left off yesterday. We're going to look at vertical asymptotes. We're going to look at further technique for finding a limit, namely squeeze theorem. It's just one technique, so I'm not sure why I used plural. Okay. And once we look at vertical asymptotes and squeeze theorem, we can briefly talk about this important notion of continuity that you'll be tested on in first semester calculus. And then maybe for kicks, we can look at an application of limit, which will allow you to maybe compute your first derivative if you've never done so before. So we can compute a derivative. Derivatives are defined as limit. You can think of them as an application of the limiting process. Okay. So are we ready? All right. So vertical asymptotes are vertical lines which are not part of the graph of the function, right? Just vertical lines which your graph will approach. Okay. And so vertical lines all have the equation of the form x equals some constant. Because this line, every point in this line is defined by the property that x is that constant, but y could be anything. So since y could be anything, if you just vary y, you get an infinite. So our vertical asymptotes are going to be of the form y equals some constant. All right. Okay. we have 4 graphs here. Okay. And what we want to do is make some observations about these graphs. 8 minutes. Right, so the first graph is the graph of the equation y equals 1 over x. And we notice that x equals 0 is indeed a vertical asymptote here. But what you want to observe here, and in fact all these graphs, is that a function's behavior can be different, depending on which side of x value we're on, right? So in the first graph, if we're to the right of 0, we would say that the function grows without bound. Its limit as x approaches 0 would be infinity. But from the left side, the function goes to negative infinity. So the behavior on either side the function can behave differently depending on which side of the x value you're on. Or it could be the same, right? Like so here, doesn't matter whether x is approaching 0 from the left or the right. It looks like in the graph, the function blows up. So its behavior is the same on either side. It can even be more wild, right? Where maybe, well, by the way, this is, I believe, the graph of the equation y equals 1 over x squared. Maybe you want to start thinking about the difference between these two. The third graph over here is actually the graph of the equation y equals e to the power 1 over x. We'll see that as an example, I hope. And so here what you want to notice is that the limit, as we approach 0 from the left, exists, and it's equal to 0. Yeah, the graph of our function, the y values of the graph approach y equals 0. But from the right, as x approaches 0 from the right, the function goes off to infinity, positive infinity. So it's possible that on one side of an x value, namely 0 here, the limit does exist, but on the other, as we approach 0 from the opposite side, the limit might be infinite, might not exist. And of course, in the last example, which is something we will look at, it's actually the graph of sine of x over y equals sine of x over x. So here, well, I mean, the function is not defined at 0, right? When x is 0, you're dividing by 0. But turns out that as you approach 0 from either side, right, from the left or the right, the value of the y values of this function will approach the number 1. Okay. So the observations are, or just notes, I guess, that a function can behave differently depending on what side of an x value we're on. Or the same. It can be different. The behavior could be different or the same. And to address this issue, we would have to develop a notion of one-sided limit. And you can remind me, did Elliot talk about one-sided limits yesterday? So we want to talk about, develop a notion of a one-sided limit. Did Elliot say anything about one-sided limits? We'll review it if he has. Okay. Another issue would be, well, for which of these four scenarios would we say we have a vertical asymptote? We already kind of see that, like for the first two graphs, you have 1 over x and y equals 1 over x squared. Okay. All right, we'll see. We'll review one-sided limits. And clearly, we have vertical asymptotes for the first two graphs. And we don't have a vertical asymptote for the last one, right? So the only ambiguity, point of confusion might be this third graph, and the answer will be yes. We'll define a vertical asymptote using limits where the graph of y equals e to the 1 over x does have a vertical asymptote. So this is, we do have vertical asymptotes for these three graphs. So we need to develop, come up with a good definition, limit definition of vertical asymptote that will qualify the first three graphs to have them. And I mean, the reason we need to use limits is because it's situations like these, right? We're no longer dealing with like algebraic functions, like polynomial divided by polynomial with square roots and whatnot. We're dealing with other broader class of functions where the kind of pre-calculus tools that you've learned are no longer sufficient to really tell you whether you have a vertical asymptote or not. So we have to use this calculus notion of limits to define asymptotes. Another thing that you're going to be expected to distinguish, make a distinction between are if a limit is infinite. So if the function goes to infinity or minus infinity, you have to just make a distinction between which one it is, right? Is it plus or minus infinity? So you're going to have to develop skills that allow you to analyze the sign analysis, essentially, to figure out whether a limit is plus or minus infinity. Right, so that's another question we'll have to answer. All right. So that was just some motivating graphs for the issues at hand. So let's go ahead and first define one-sided limits, or at least review them. Okay. Because a function can behave differently depending on which side of, let's say, x equals a we're on, right? So if we're to the, let's say, left of a, okay, and we want to know the function's behavior, we could write, well, let's look at the limit as x approaches a. However, we need to somehow come up with a notation that indicates that where x's are approaching a from the left side, or if you'd like, from the negative side of the number line. And so the notation you'll learn is that there's a superscript there with a minus. Okay, the minus just means we are approaching a, but from the negative side of the number line. From the left side, we're on the left side of a, right? So this means that x is slightly smaller than a, to the left of a. And then we write down the name of the function whose behavior we're analyzing. And it looks like as the x's approach a from the left, the corresponding values of the function, the y values, look like they're approaching some number L. And from the other side, if you want to analyze the behavior of the function, you'd write limit as x approaches a but we want to then indicate that we're approaching, the x's are approaching a, but from the positive side of the number line, right? From the right side. So that's x is going to be bigger than a. So to do that, we'll just use a superscript of a plus to indicate on the right side of a, from the positive side. And you see over here in this picture, at least, as the x's approach a from the right, the values of the function approach some number r. And the limit from the left does not necessarily have to equal the limit from the right. So the function can behave differently depending on which side of a we're on. And it can get even worse, of course. Right here, that's an example where if we look at the limit of our function as x approaches a from the left, the negative side of the number line, we see that our function's values grow without bound. So we say our function goes to positive infinity. But from the opposite side, you'd write x approaches a from the positive side of the number line. Our function then, according to that graph, goes off to negative infinity. All right, so if the function has different limits, right, from either side, depending on which side of a we're on, does it make sense to write limit as x approaches a? All right, exists, right? Does that make sense? It doesn't, because when you write limit as x approaches a, without indicating whether x is approaching a from the left or the right, you're implying, you're communicating to your colleagues, your grader, that it shouldn't matter, right? It doesn't matter whether x is going to a from the left or the right, the function should behave the same. So if the limit from the left and the right disagree, then we don't write the limit exists, right? So the only time you would say that the limit exists is if the limit as x approaches a from the left is L, whatever, and the limit as x approaches a from the right is also the same number L. So if the two one-sided limits agree, then it makes sense to say that the limit as x approaches a, without having to indicate whether x approaches a from the left or the right, exists, right? And it's equal to L. So you learn that for a limit to exist, the limit from the left and the right will have to agree. Also, can I ask you a conceptual question? In this picture, does f of a have to exist for the limit to exist? I bet I get some calculus veterans who know this answer right away. Right, of course I do. And why not? Can anybody? Yes, right. So we just want to emphasize that limits tell you how a function behaves around an x value, right? So we're close to a. We don't actually have to get to a at all. So it's possible if the function is not defined at a, right, or it's something crazy, but for limit, we just care how the function behaves around a, not what happens at a. And again, calculus veterans, perhaps you know the word that we use when how the function behaves around a actually matches what the function does at a. It's going to be one of our topics today. Like, right, so again, well, never mind. Maybe that's too abstract of a question. All right, do I need to mention anything about, but we talked about one-sided limits and what it means for a limit to actually exist. So we'll look at, we're just talking broadly about one-sided limits. So we're going to do some examples here. And let's consider this function in the first example. And we want to describe its behavior around x equals 2. First of all, is the function defined at 2? No, it's not. Why not? Well, of course, the denominator, if x is 2, you'd be dividing by 0, so no. Is this okay? And so then to further investigate behavior, we might start taking limits, but we won't go into saying, let's find the limit as x approaches 2, but rather let's take the limit as x approaches 2 first from the left. So we're going to investigate the left side of the limit. Here's f of x. Okay, and what concept will we have to use in order to try to evaluate the limit? Of course, we can't just plug 2 in for x to get the limit, because we would get the indeterminate form 0 over 0. So we might have to do some simplification first. I think Elliot discussed this yesterday. What's the definition of the absolute value of some, let's say, call it u for now, right? So sometimes it's hard to do absolute algebra with absolute value. So we can put in the absolute value for a piecewise function. And we know that if u happens to be positive, or at least not negative, in the first place, the absolute value of u is just u, right? Like absolute value of 2 is just 2. However, if the thing inside the absolute value is negative, okay, like let's say u is negative 2, of course, finding its absolute value still gives you a positive 2. So what we do is, in that case, if we know that u is negative, we just negate the thing that's known to be negative, and that would end up giving you, right? You negate the thing that you know is negative to give you the positive result that absolute value would give you. Okay. So with absolute values, when evaluating limits, you might have to use this idea of replace absolute value of u with the 2 cases where u is positive, you get u, or where u is negative, in which case the absolute value of u is just the negative of that negative u. So can I ask you, absolute value of x minus 2, I guess, would be x minus 2. For which values of x? What would have to be true about x for us to say that the absolute value of x minus 2 is the same as x minus 2?
X larger than 0?
X minus 2, the thing inside the absolute value, would have to be greater than or equal to 0. That's right. Let's just replace x minus 2 with u, right? And that's the same thing as saying as that x has to be at least 2. So when x is greater, or let's say at least 2, absolute value of x minus 2 would just be x minus 2. X minus 2 would be positive in that case. And the absolute value of x minus 2 then would be the negative of x minus 2 in the case where the thing inside the absolute value is negative, less than 0. Another way of saying that is that x is less than 2. So for the case where x is, right, to the left of 2, x is smaller than 2, the absolute value of x minus 2 just be the negative of x minus 2. So it's a concept you'll definitely be seeing. All right. So back to this limit, right? Since x is approaching 2, but from the negative side of the number line, which side of 2 are we on? Are we to the left of 2 or to the right of 2? When x is approaching 2 from the left, right? X would be to the left of 2. So x will be slightly small, will be smaller than 2, which means that we can replace the absolute value of x minus 2 with the negative of x minus 2. And now we can do a cancellation. X minus 2 divided by x minus 2 is 1, but we are left with the negative 1. And the limit of a constant, right? This just remains negative 1. It doesn't care what x does or doesn't do, so the limit of that is, as x approaches anything really, is just negative 1. So next we'd want to consider the limit as x approaches 2, but this time from the right, the positive side of the number line. So since x is approaching 2 from the right side, right, the positive side of the number line, you see that x is bigger than 2, which means that the absolute value of x minus 2 is just x minus 2. So that's where we do our simplification. This reduces the constant 1, and the limit of a constant is just that constant. Okay, beautiful. So here we see that the limit as we approach 2 from the left is negative 1, but from the right it's positive 1. In fact, you might be familiar with the graph of this function. It looks like there's this jump. So, okay, so the limit from the left and the right do not agree. They're different. So can we say that the limit exists in general? So are we able to write confidently that the limit as x approaches 2? Oops, I drew it in the wrong place. I apologize. So no, right? So this would make no sense to say the limit as x approaches 2 of my function something, because it's not, it depends on which side of 2 you're coming from, right? So this just does not exist. And I forget, I should have written down which, well, let me slow down here. Okay. You know, let me factor this really quick because I forget which, I think it's, I was going to consider the behavior as x approaches 2 here. Yeah, okay. So again, we're just going to look at the limit here. Does the limit as x approaches 2 exist? Well, to answer that question, we could try to just evaluate the limit directly, and we would run into the problem you'll run into 80% of the time, right? That you would get 0 over 0, which is, well, anything could happen, right? That's just meaningless. So to answer this question, we might have to, well, do some algebra. Okay. And the answer turns out to be, yeah, the limit exists. Maybe not an example for one-sided, because these do cancel, like, and we would get 6 over 3, so that's 2. So I think this is an example where our graph simply has a hole, our function is not defined at x equals 2. In fact, I think there's turns out there's a asymptote at -1. But the limit nevertheless exists, because when we did the algebra, it didn't really matter. This result didn't depend on whether x approached 2 from the left or the right. Maybe not the smartest example I wanted to look at. Okay. All right. So we mentioned one-sided limits, and that the limits, the two one-sided limits, would have to agree before we can say that the limit in general exists. We now want to formally define vertical asymptote, right? So x equals a, which is the graph of that equation is a vertical line in the xy plane, is a vertical asymptote. As soon as one of these conditions hold. So the limit as x approaches a from the left is either plus or minus infinity. It's an infinite limit, whether it's plus or minus, or the limit from the right, as x approaches a from the right, is plus or minus infinity. So as soon as just one of the one-sided limits is an infinite limit, be it positive or negative, we have a vertical asymptote. And that allows for the so that allows for having a vertical asymptote because the function like goes off to infinity from both sides, right? Goes to infinity from, let's say, positive infinity from one side, but negative infinity from the other. And it also allows for the possibility that the limit exists from one side, but is infinite on the other side. So as soon as just one of the one-sided limits, an infinite limit, we say we have a vertical asymptote. So maybe now what we want to do is maybe practice using this definition of vertical asymptote, where we don't have a graph, but we just need to do some algebra, figure out the one-sided limits to see if at least one of those one-sided limits is an infinite limit. And in your class, they will ask you to find both one-sided limits. And you will have to know whether that limit is a positive or negative limit, right? Or positive infinity, negative infinity, if it is an infinite limit. And let's look at just the two examples that the two graphs we started with. And so this is sort of kind of like Elliot was doing horizontal asymptotes, so he was considering what happens as x goes to infinity or x goes to negative infinity. What we'll be doing instead is computing limits here. So as x approaches 0 from the right, 1 over x goes where? It goes to positive infinity. And I hope you can see why. Right, if anytime you have a non-zero number, divided by something that goes to 0, your limit is going to be infinite. It's kind of like, well, okay. You can do a little thought experiment if you haven't done this before, but fix the numerator and then make the denominator smaller and smaller, and what you'll find is that the numbers you get are larger and larger in your calculator, or if you want to do some arithmetic there. So this is just getting larger and larger, right? That's 10, that's 100, 1,000, and so on and so forth. Okay. So this is going to be plus or minus infinity. Okay. And what we have to do is be able to say whether it's plus or minus infinity. So we can think of this as saying, well, the numerator stays at 1, but the denominator goes to 0. However, since we're approaching 0 from the right, as this plus indicates on the positive side of the number line, we know that the denominator doesn't actually get to 0. It's slightly to the right of 0. So it's a slight positive thing. So we have positive divided by positive, right? And that's going to be positive 1 divided by something that approaches 0 but is still positive, something that goes to positive infinity. Now, on the from the other side, if you let x approach 0 from the left, it's like 1 over x is going to go to negative infinity in that case. Right? Because we still have the situation where the numerator is fixed at positive 1, but the denominator goes to 0, but x is just approaching 0 from the left, so x is slightly negative, not quite 0. So you have the situation, you have a positive numerator divided by negative denominator, so this would be negative infinity. So what we do is we do sign analysis, right? We carefully look at the factors and check whether they're positive or negative. In fact, I think you can write down a general rule, right? So the limit as x approaches 0 from the right, so x is going to be slightly positive, of 1 over x to an odd power is going to be positive infinity. However, the limit as x approaches 0 from the left of 1 over an odd power, like, 1, 3, so in case you forget, odd integers are positive integers, these are 1, 3, 5, 7, so on. Will be negative infinity. That's because a negative number, an odd power, is negative. Right? Right. So, by the way, in the first example, do we have a vertical asymptote? And if so, what is it, right? Yeah, we do. I mean, at least one of the one-sided limits was infinite. In fact, both of them were. So we can say that x equals 0 here is a vertical asymptote for the function f. Now, if you have, for the next example, if you have something of the form like a non-zero number divided by x to the even power, the limit is going to be positive infinity from the other side as x approaches 0. That's because you're squaring something there, right? So a number squared can never be, a real number squared can never be negative unless that number is 0 itself. So you have the same situation where the numerator is stuck at a positive number, but the denominator, well, is getting close to 0 and being squared, and it's still a positive 0, right? Sorry, it's a number that's approaching 0 but still positive, so you're going to get a positive infinity, positive divided by positive. And if x approaches 0 from the left, it doesn't matter, right? Because you're squaring the denominator. So a number squared will not be negative. So you still end up with 1 over something that's slightly negative, but squared makes that a positive, right? So positive over positive still gives you a positive infinity. And 2 is an even number, and it turns out that, you know, this kind of rule holds for even power, integer even power. This would be plus infinity. All right. And so here, both of the one-sided limits are infinite, but it doesn't matter as soon as one of them is. You can say that we have an asymptote, x equals 0 is a vertical asymptote for our function. So this is a slightly more fun example. So let's see what happens. For this, I guess we would have to kind of coordinate the graph of 1 over x with the graph of the exponential function. Right, and we're going to see whether x equals 0 is a vertical asymptote or not. Right, that's x equals 0 is a candidate because if x is 0, you'd be dividing by 0 over here. So that's always a candidate for a vertical asymptote. Just a candidate, not necessarily a vertical asymptote. So suppose we try to compute the limit as x approaches 0 from the left side of 0. So let's reason this. So as x goes to 0 from the left, what can you say about 1 over x? Where does it go? So x is approaching 0 from the left. So 1 over x goes up to negative infinity. Remember that we have 1 over something that goes to 0, but it's slightly negative. So it's positive over negative, so that's like negative infinity. Okay. Now, this 1 over x is just the argument of our exponential function over here, either the 1 over x. So as the argument of the exponential function, the 1 over x, since that goes to negative infinity, right? we can then look at the graph of our exponential function and say, well, what happens when the argument of our exponential function goes to negative infinity? It looks like e to the x is approaching the value of 0. So as 1 over x goes to negative infinity, e to the 1 over x goes to 0. Okay, so the limit would be 0. So the limit from the left is 0. All right, and let's follow the same similar thought process. Let's let x approach 0, but this time from the right. So x is slightly positive. What can we say about 1 over x? So as x approaches 0 from the right, it looks like the y values on this graph of 1 over x go positive infinity. Okay. And this 1 over x is just the argument of our exponential function. So as the argument of the exponential function goes to positive infinity, our exponential function blows up. Positive infinity. Oops. So the limit as x approaches 0 from the right of this funky function is positive infinity at the end of the day. Okay. So we've computed the two one-sided limits for this function. So is x equals 0 a vertical asymptote or not? Well, yes, right? Because we said that using limits, the definition is that as soon as just one of the one-sided limits is plus or minus infinity, then we have a vertical asymptote. Well, I'm gonna have to skip these two next examples. I'll let your professors. Well, this one, we'll skip these because it's too long. So, but I guess the summary is for finding vertical asymptotes, find where you have a denominator with the denominator 0. Those are your candidates. So that's where the denominator is 0. I mean, there's some other things like for logs, right? And then compute the one-sided limits. So they're going to be two of those. And if one, at least one of those one-sided limits is plus or minus infinity, then we have a vertical asymptote. If the limit from both sides is not, well, from either side is finite, then we don't have a vertical asymptote. guess any questions? We didn't do too much algebra here, but any questions about conceptually what a vertical asymptote is and why we want to talk about it using limits? All right. So now we're going to leave behind vertical asymptotes specifically and just talk about another technique for finding limits. And this technique is called the squeeze theorem or sandwich theorem. And the idea is this, that if you have a function and you want to find the limit of it as x approaches a, say, right? So here our function is in orange. And you want to know, well, what is this? If you're able to sandwich your function, let me just write this in black, it's ridiculous, okay. So if you're able to say that your function is between two other functions, you have the lower bounding function, which is in green, and an upper bounding function, which is in blue. Okay. And this happens near x equals a. Let's say it's a local phenomena. It's possible that these three functions might start intersecting somewhere else, right? Maybe f becomes larger than h, whatever, but further on. But at least near a, we have this, if you zoom in, we have this situation where our function, f in orange, is sandwiched in between two other functions. So if you have this situation and the limit of the two bounding functions, g and h, exist and they agree, so you can see that as x approaches a in the graph, the limit of the blue function is L. Likewise, the limit for the green function is the same number, L. Then obviously, I hope it's intuitive that the function that's in between, the orange function, must have the same limit. It must go to the same place. Okay. So if you have these two conditions satisfied, then we say that the limit of the function, our function is being squeezed to have the same limit. Okay. So where you use this squeeze theorem is where you have a somewhat complicated function f of x, but you can somehow set up, you can bound your function, right, between two simpler functions whose limits are easier to evaluate. And if those limits exist and go to the same place, then the thing in between, our more complicated function, must have the same limit. That's the idea. So let's look at examples. And we want to be able to compute the limit as x goes to 0 of x squared times cosine of 1 over x. And the reason that this is right, the issue is that as x goes to 0, 1 over x is going to go to plus or minus infinity, right? And that makes no sense. Like, what's cosine of plus or minus infinity, right? It's just, there's no such animal. Cosine doesn't have a horizontal asymptote. So we're going to try to analyze this situation, and maybe we can think about this. Let's say if we look at, think of this as two factors, right? If you look at just the first factor, which is x squared, as x goes to 0, where does x squared go? Well, it goes to 0. You can just evaluate directly. And what do we know about cosine? Right? Well, I do know that cosine, whatever the argument of cosine is, I do know that it oscillates between plus and minus 1. As we say, a cosine is bounded between plus and minus 1. And it doesn't matter what you plug into cosine. What cosine returns is always some number between negative and positive 1. And so I can think of so you can think of this as like cosine just keeps oscillating between plus and minus 1, but x squared will go to 0 as x approaches 2. So you can think of that as like a amplitude that's changing with x. It's a function of x. It's an amplitude that decreases as x approaches 0. So you can imagine your cosine is oscillating, but the amplitude of x squared would go to 0 as x approaches 0. So you can almost kind of see the two bounding functions there. So we're going to use squeeze theorem, and we're going to start with, as you often do when you see sine or cosine, and you're in the section involving squeeze theorem. If you see sine and cosine, you can think of starting with this fact, that sine or cosine in general are between negative and positive 1. So if you're using a squeeze theorem, this is often the inequality or the inequalities that you start off with. And what we want to do is we want to be able to find our function squeezed between two other functions, right? So what can we do in order to get x squared times cosine? Well, we can just multiply everything by x squared, which is not negative, so we don't have to change the equality. So just multiply all sides, if you will, all pieces of this inequality. So multiply by x squared. The first piece, the second piece. Since you're multiplying by a positive number, that's not going to change the direction of the piece. Okay. So you have sandwiched your function between two other functions. And we're looking at the limit of, now we can take the limit of all these guys as x goes to 0. Right, and notice that the two limits on the outside are easy to compute. You just can plug in 0 for x directly to get 0. So it looks like the limit of our function, x squared times cosine, is some number between 0 and 0. So it must be 0 itself, right? So by squeeze theorem, so that's just an example of, I guess, the thrust of a squeeze theorem problem. You start with an inequality, multiply stuff so that you see your function sandwiched in between two easier functions, take the limits, and if the limits outside agree, then the limit of your function must be the same. It must go to the same place as the two bounding functions. All right. Now, so by the way here, x equals 0 in the previous example here, x equals 0 is a candidate for a vertical asymptote. That's because when x is 0, we'd be dividing by 0. And so we took the limit as x approaches 0, and we got that the limit is 0. So is x equals 0 a vertical asymptote? No, right? That's because the limit wasn't infinite or from any of the sides. The limit exists and it's equal to 0. Okay. The next example is, well, can you intuit what this limit should be? So as x goes to infinity, positive infinity, again, we can maybe think of this as origin being an amplitude like that varies with x. It's 1 over x times sine of x. And x is getting large, right? So you kind of know the graph of sine. It just oscillates between plus and minus 1. And as x gets large, this 1 over x gets small. So while this factor just keeps oscillating, this variable amplitude vanishes, right? It goes to 0. So like this graph would look something like a combination of these two. No, I don't know what happens. Actually, I do know what happens there. But you would get something that keeps oscillating because of the sine, but with a decreasing amplitude because of the 1 over x multiplying the sine. So okay, I should have changed the settings there. It looks like one of these buttons is the undo button. Yeah. All right. Well, maybe I'll just say that's a lost battle. No, okay, it's a lost battle. Must be a. Yeah. All right. That's a lost battle. So we expect that this limit is 0, right? So this infinite limit is 0, so y equals 0 is a horizontal asymptote. Because it's a limit at infinity, right? Yeah. But you're going to be expected then to prove this. And, sine of x over x, sine of x is not a polynomial or algebraic function, so you can't use the technique of divide the top and bottom by the largest power of x because it doesn't do anything, right? So you might use squeeze theorem even at infinity. Okay. So you can start with the fact that sine of x, always returns a number between negative and positive 1. Sine of x is bounded by those two numbers. And x is going to infinity, so x is positive, 1 over x is positive. We can just multiply everything, each piece in this chain of inequalities by 1 over x. So next we can take the limit of each of these pieces as x goes to infinity. So the limit of the two outside functions is clearly 0 because we get a finite number divided by something that goes to infinity. That's something that will go to 0. So then we cite make sure the grader knows that we're going to cite the squeeze theorem at infinity. Okay. So you can even use squeeze theorem if x is not, is going to infinity or minus infinity. All right. I'm going to move on to the more interesting, the so-called special trig limit. And we're going to prove. All right. So by the way, so this is a meme. It's false. It's a joke that between engineers, physicists, and mathematicians, right? So can somebody? So this is wrong, or not precise, not exactly right. It might be approximately right, right? So the correct thing to say is that sine of x is approximately equal to x. But what has to be true about x? Does anybody know? For sine of x to be approximately equal to x, what has to be true about x? So, all right. Well, here's a period of sine. Here's the graph. And also we can draw the line y equals x. So in this picture, when is x approximately equal to x? Where? What would x have to be close to? Let me put it that way. When is the line y equals x? Give you approximately the same thing as y equals sine of x. Okay, thank you. Right. So obviously at x equals 0, sine of 0 is 0. But we can make an approximation to say sine of x is approximately x for small, whatever that might mean, values of x. So x is near 0. And so you see this in physics and engineering all the time. That's why this is a joke, right? Where you just say, well, use a small angle approximation, sine of x in our equation just becomes x, and everything's solved, right? Mathematicians are like, hold on, It's not exactly right. All right. So we would expect that sine of theta over theta, as theta goes to 0, should be kind of close to, since theta is close to 0, it's approaching 0 after all. Sine of theta is almost like theta. My gosh, sorry. So we know that that will reduce to just 1. And so we expect this limit to be 1 if this approximation is valid. And it turns out it is. So we're going to learn that they're going to, before L'Hopital's rule, because they don't explicitly not allow you to use L'Hopital's rule initially. You'll have to know that this special trig limit, sine of theta over theta, as theta goes to 0, is 1. Goes to 1. And before we prove this, maybe you can tell me What if we have something like limit as theta goes to 0? Let's say sine of 5 theta over theta. What do you think that's going to equal? Okay. Using a small angle approximation, right? Theta is close to 0, which means that 5 times theta is also close to 0. So using a small angle approximation, you see that sine of 5 theta should be approximately 5 times theta. So this would be 5. And that's what we expect to be true. So, right, anyway, and yeah. So you often kind of eyeball these limits by using small angle approximations. Okay. What we want to do is kind of prove this special trig limit using squeeze theorem with an exercise in trigonometry. Okay. All right, so we have a unit circle here. And so being a unit circle, we know that the radius here is 1. And let's call this angle theta that our radius makes with the positive x-axis. And if you extend the radius, well, you have the radius and you draw a line that's tangent, that just kisses the circle there. There is a fact from geometry that the radius is going to be perpendicular with any line tangent to the circle. Right? So this is a 90-degree angle. And we can drop a perpendicular here to get another 90-degree angle. We want to prove this special trig limit by using squeeze theorem, and in order to do so, we want to look at this length compared to this length compared to this length. And you can also use actually areas, but never mind that. Okay. So what expression using our figure here would give you the length of the orange segment, that vertical segment, in terms of theta? So I guess what expression would give you this length in terms of theta? Yes. Let me see who's raised their hand. Let's see. Well, this is a right triangle with radius 1, or hypotenuse 1, and we're looking at the operations on the opposite side relative to this angle. So the sine will do the job, right? Sine of theta is the opposite side divided by the hypotenuse, which happens to be 1. So the opposite side is just given by sine of theta. Does anybody know in a circle if this is theta and we have a radius r, does anybody know the expression for the length of this this part of the circumference? Right. So if the angle is 2 pi, if the angle is 2 pi, if theta is 2 pi, then you've gone all the way around, right? And then the length we're referring to is exactly the circumference. And the formula for that circumference is 2 pi times radius, right? It turns out that in general, if you want to know the length along the circumference of a circle of a radius r, defined by angle theta, it's just the radius times the angle theta, where theta has to be in radians, if you haven't seen that before. So that's exactly what this green part will be, right? It's part of the circumference defined in a circle of radius 1, defined by this angle theta. So that length must be r, which is 1 times theta. So that's just theta in radians. So pi diameter theta 2 divided by 2 pi. Diameter is 2. Yeah, that makes sense. That Hania, whatever you got that formula, the way you thought of it, it does give you the correct result. So you would have to, I guess, combine the math out and explain how you thought of that. I think I know. I think you probably said something about the ratio of theta. The ratio of theta to the total angle in a circle, which is 2 pi radians, should be the same as the length we're looking for along the circumference to the total circumference. And 2 pi's cancel, and you would indeed get that length, after you multiply both sides by r, is r theta. That's not a bad way to think about it. I like it. Okay. So finally, the blue segment. We're almost done with this one. Sorry. But it's the kind of connection between, in calculus, it's limits, but before you do limits, you have to typically set up some simple geometry or trigonometry. You have to kind of have enough knowledge to be able to set up something before you take limits. Right? This is the kind of game we play. Finally, we have another right triangle. Ugh, terrible. Okay. Where this side is length 1, so I'm thinking about this side is 1. Then we have the blue side. Okay. And here's our angle theta. So can we express the blue side as a function of theta? Can we express that length in terms of theta? Think of trig functions, right? You have angle theta. You know one of the sides has length 1. Okay. And that side happens to be adjacent to our angle theta. Right, so this is the adjacent side relative to our angle. And we're interested in the side that's opposite our angle. Opposite. So which trig function will relate opposite side to adjacent side? All right. Well, tangent, right? So we can reason that, okay, well, tangent of theta is the opposite side divided by the adjacent side, which happens to be 1. So the opposite side is exactly tangent theta. All right. That won't really, okay. So I hope then it's obvious that, well, okay. Let's just use our common sense, let's say, and then the orange segment we see is going to be shorter than the green curve, right? So sine of theta should be smaller than theta, right? I'm comparing the orange to the green lengths. So this is in terms of length. Okay, and theta, in turn, will be smaller than tangent theta. So the green length is shorter than the blue length. So using the first inequality, if we divide both sides by theta, notice I'm assuming theta is positive, we get that sine of theta over theta is less than or equal to 1. And over here, I guess we can multiply both sides by cosine and also divide by theta to get that cosine of theta is less than or equal to sine of theta over theta. So using these two results, we can then squeeze our function sine of theta over theta. So it looks like sine of theta over theta is at most 1 and at least cosine theta. So now we can take the limit as theta goes to 0. As theta goes to 0, cosine will go to 1. Cosine of 0 is 1. That's unfortunate. All right. So according to the squeeze theorem, sine of theta over theta as theta goes to 0 is a number between 1 and 1, right? It's going to go to 1. So that's a proof of the special trig limit, that L'Hopital's rule. I mean, we didn't tell you the whole truth here because we didn't consider what happens when theta is negative, but if you want to get into the details, we'll get the same limit. Okay. But that's a typical calculus 1 game, right? Geometry, trigonometry, set up some stuff, and then take limits or take derivatives or something like that. Is that it? Oh, okay. And so after they introduce that special trig limit, then you're going to be expected to see when to use it. So for example, in this problem, x goes to 0, we have tangent of x divided by x. So where would our special trig limit show up here? Like, I don't see it immediately, right? But can we somehow rewrite tangent so that we start seeing the special trig limit? Well, if we realize tangent is sine divided by cosine, we could rewrite this as sine of 5x divided by cosine of 5x. That's our tangent times x. I'll just write it over here, right? And then you start thinking in terms of factors, right? You say, well, this is sine of 5x over x times 1 over cosine x, 5x, sorry. And we know we can do this because when you multiply fractions, you just multiply the denominators together here, right? So that would give you x times cosine. And you'd multiply the numerators, so it just gives you sine. Still the same. And we note that this factor is not really an issue. This is not an issue as x goes to 0 because as x goes to 0, 5 times x also goes to 0, and cosine something that goes to 0 is something that goes to 1. So this factor is not a problem. We're just going to get 1 divided by 1. It's the first factor that's an issue, in the sense that if you evaluate directly, you get 0 over 0, but we see that we can use our special trig limit. But before we do that, yeah, I should have mentioned that when using the special trig limit more generally, right, you have to have in the denominator there exactly the same thing as what's inside of sine. These have to match before you get to use the special trig limit. And the thing inside has to go to 0. So then you're going to learn, okay, I have sine of 5x, so I would need to see 5x in the denominator as well. So you'll learn that you have to introduce factors, right, if you need them. So we can just multiply the top and bottom by 5. And now we can have, the limit of 5 as a constant. It's just 5. Save time. And the limit of the next factor, the limit of the next factor using our special trig limit would be 1. And the limit of the third factor here is just 1 over 1. So 5. Okay. Right, so you'll be manipulating stuff so that you can use your special trig limit. I guess the only reason to do this example here is just, again, if you evaluate directly, what would you get? 1 minus cosine of 0 divided by 0 squared. So cosine of 0 is 1. 0 squared is 0. So you'd get 0 over 0. So that's the determinant. 4. Well, yeah. So this is, is everybody familiar with this Pythagorean trig identity? It's Pythagorean in the sense that of, the a squared plus b squared equals c squared, but for a unit circle. So maybe, yep, right. Of course, that should be obvious from a unit circle. We know that in a unit circle, the x coordinate is cosine theta, y coordinate is sine theta. That's a right triangle, so Pythagorean theorem holds. The sum of the two smaller sides squared is equal to the hypotenuse squared. Right. So if I subtract sine squared from everything, you'll be using this trig identity, this Pythagorean trig identity, and its cousins, I suppose, its derivatives, quite often. So cosine squared is the same thing, or I should say, subtract cosine squared from both sides. We'll get sine squared is 1 minus cosine squared. Okay. And notice that this gives you a difference of 2 squares. So 1 minus sine squared we can factor as 1 minus sine times 1 plus sine, right? That product of conjugates. Likewise, for 1 minus cosine squared, that's a difference of squares. You can factor as a product of conjugates. So this suggests that if you have 1 minus cosine, you can replace that. You could replace that with a single term if you had 1 minus cosine squared, right? 1 minus cosine squared is sine squared. So this suggests that we can deduce that by multiplying the top and bottom by the conjugate. So you've already multiplied by conjugates on top and bottom to get rid of square roots. But now you will learn that you can multiply by conjugates to introduce the Pythagorean trig identities so that you can simplify. You probably would not. So at the beginning, so somebody's asking if you would get credit if you use L'Hopital. I do not use L'Hopital. Learn some of the multiplying the numerator there, or the factors in the numerator, you get a 1 minus cosine squared. Okay. We used our Pythagorean trig identity. And then we're going to think of this as sine squared over x squared times 1 over 1 plus cosine x. Again, anticipating that as x goes to 0, this factor over here is not a problem. Because x goes to 0, cosine becomes 1. But for the first factor, we will have to use our special trig limit. You can think of it as sine x over x, quantity squared using properties of exponents. Okay. So now the limit here of the first term will just be, this goes to 1 by our special trig limit. And then other factor goes to 1/2. Or I should say, cosine of 0. As x goes to 0. So you get 1 plus 1 times 1/2, I should say. So the limit turns out to be 1/2. Okay. All right. Let's not do any more examples of that. So that the only reason that was worth pointing out is that you should, I guess, review your trig identities. Maybe I'll touch on this. We won't do any examples, I suppose. But we want to talk about this notion of continuity, which is something that a function has to satisfy in order for a lot of theorems and calculus to work. All right. So let's define continuity. So first of all, continuity is something that happens for a function at a point. So we say f is continuous at x equals a, or it's not, right? It's something that happens at a point. And we say that f is continuous at a if the limit as x approaches a of our function is equal to what the function does at a. Now, if you break that up, what does that mean? So the left-hand side here, the limit has to exist for us to write this. So one of the components to have continuity is that this limit must exist. This will just tell us that the function has a limit which is finite, and it's the same from either side of a. So the function behaves around a, right? This behaves the same way around a, regardless of which side of a we're on. So the limit must exist. Okay. The right-hand side over here, well, if you write that implies that f must be defined at a. It must exist there. And the this is like the left-hand side. This is like the right-hand side. And this is the equality. So what that says is that, whereas the left-hand side says how the function behaves around A, the right-hand says what the function actually does at A. Continuity must have this equality that says that how the function behaves around A must match what the function does at A. So this is where we must have that equality. So how the function behaves around A matches what the function actually does at A. And so students typically think of continuity for a function as it's a function whose graph is nice and connected, even though that's very loose, but still, I think it works for calculus 1 and 2. Right? There's no disconnection in the graph. It's continuous. It's connected. It should be not a hole. That's right. So when we say that f is defined at A graphically, there should be not a hole. Okay. So, right. So like the limit is like anticipation, right? And what the function does at A is like culmination, and you want those to agree to have continuity. So if I scroll up, I actually have 4 graphs, all of the functions, all of which are discontinuous. They're not continuous at A. And so you'll be asked to specify y function for which reason, which of these 3 reasons, which of these 3 reasons do we have a discontinuity? So these are, we have discontinuous functions at A. Okay, so the first graph is discontinuous A because of which reason, right? Right, graphically, maybe I need to zoom in, but just for a second, there's a hole. So as somebody already mentioned, that means that f is not defined at A. Now you have to do this algebraically and graphically, so recognize the reason a function is discontinuous graphically, and then also later on do it algebraically. So we have continuity there. Now for the second graph, the function at A, so you have to be careful here, there's a hole and a solid, right? So does f of A exist? Well, if you draw vertical lines at x equals A, you'll hit the graph where the solid, the filled circle is. So that's f of A. So it does exist. So the first reason works out. I mean, the first condition holds. The function is defined at A. But the second condition does not hold, right? Remember that for a limit to exist as x approaches A, that's equivalent to saying that the one-sided limits exist and they agree. Okay. Here the limit from the left is one thing, and from the right it's a different thing. Right? There's a jump there, so the limit doesn't exist. It's different on the side. So the function cannot be continuous there. There's a break in the graph, a disconnect. Here, likewise, the limit doesn't exist because one of the limits is infinite. So we can't have a continuous function. And the last case is like the kind of contrived case where they'll give a piecewise function. But notice that the function at A, if you draw a vertical line at x equals A, you'll hit a graph, point that's on the graph. So f of A exists. And as x approaches A from either side, the function seems to be approaching the same y value. So the limit exists, But there's still a disconnect. That's because even though the limit exists, okay, and the function at A is defined, they don't match. So how the function behaves around A does not match what the function actually attains at A. So we still have a discontinuity. So this is for the third reason, right? We don't have that equality. And again, it's going to be important because a lot of true statements in math depend on a function being continuous. And, make a fuss about it. All right. But we're not going to do like analytic examples. We have 8 minutes. Okay. So maybe we won't discuss the tangent line, but maybe we can compute a derivative or discuss the idea really quick. Okay. So part of calculus, right, is using simple approximations to something that's complicated. So often we will use linear approximations to a function near a point. So we kind of approximate curves with lines or line segments or something like that. So here we're going to take a point on the graph. So that would be x is A, and the corresponding y value would be, well, whatever you get after you plug in A into your function. So this point is A at A. And what we do is we want to kind of approximate this curve by picking a point near another point phi. And so we'll call that like, if you start with A and you add a little amount, let's call it H, you'll end up at an X value that's A plus H. Okay. And if you plug that value of the X, A plus H, into your function, you'll get the corresponding Y value. So this point on the graph is, well, X is A plus H, Y is at A plus H. Okay, so next we're going to draw a line through those 2 points. Okay, and what do you call a line that goes through 2 points of the graph? It's called a secant line, right? And the secant line has a slope. All right. And generically, right, the slope of the line is the change in the y values over the change in the x values. So here, the change in the x values, or the y values, I apologize, would be the, let's say, this y value minus that one, right? So it would be f at A plus H minus f at A. Okay. And the change in the x values, well, you can see it's exactly H, but you can say that it's the larger, or it's the first x value minus the second x value. That will just indeed give you H. Right, so that's the pre-calculus part. And the calculus part then would be this idea of, well, imagine we take this point over here and we move it closer and closer to this guy, right? We're fixing this point here. And we're just going to move this. Each of them has a slope given by this formula. And for our points to get closer to the fixed point, it's the same thing as saying that h goes to 0. So we're going to let h go to 0. And what happens is that as h goes to 0, at the limit, our secant line is going to become a line that just kisses the curve. So this line that results is called the tangent line to the curve. And oops. And its slope would be the result of taking the limit of this slope of secant line. So we're going to take the limit as h goes to 0. You see the issue here, why this is a limit which is indeterminate, because as h goes to 0, what happens? You get f at a plus 0, just f of a, minus f at a, divided by h, which goes to 0. So you will get 0 over 0. You'll get an indeterminate form. So then we would have to do some sort of clever algebra to get the slope of this tangent line. And the slope of that tangent line is exactly what we're going to consider as the derivative of our function. It's the instantaneous rate of change, right? As x increases, by how, at what rate is y increasing? So that's going to be the definition of the derivative, and it's a limit, right? So that's why you study limits, and then once you know that, you define what a derivative is in terms of the limit. It's just the limit of the slope of the secant lines to give you the slope of the tangent line. And this is well, beyond useful, right? You will learn. Okay. And so maybe we want to compute our first derivative if you haven't yet, using this definition. I was going to do a tangent line as well, but you know what? It's not. Let's just ignore all the other stuff. Right. So we're going to do a very simple function. Just a plain old parabola. I'll exaggerate the shape. And suppose we want to find the derivative of this function. F prime, specifically at 2. So again, it's not to scale. So this would be the point 2 on the graph, right? It's 2 and 4. And you want to find this the slope of this tangent line. So it's a line that just grazes the graph. And so we know that the derivative is defined as a limit. As h goes to 0, right? The idea is that you would add a small amount to 2 and find a point nearby, draw a secant line, write down the slope so that the function at 2 plus h minus the function at 2 divided by changing the x values of h. And then we take a limit as h goes to 0 so that at the limit our secant line becomes our tangent line. All right. Well, our function is x squared, so this would be, the argument of our function there is 2 plus h, so it's the argument squared minus the function that's 2 squared divided by h. You can try to evaluate the limit directly as much as you want. You're going to get 0 over 0 when using the limit to define derivative. And then the only algebra you can do, right, you have to use all the tricks. But here, the obvious thing to do is just FOIL the first term. So you get 2 times 2 plus 2h plus 2h plus h times h. That's 4. And if you do everything correctly, the constants should cancel. Right, so 4 minus 4, 0. So now, since all the constants are gone, all our terms have an h left in them. That's going to be an occurrence. So you can factor out an h. And now, the pesky h in the denominator, which gave you this indeterminate form, will cancel with the h in the numerator. And you'll have a very easy limit to evaluate. Right? Let h go to 0, and you're left with 4. So you're going to find that f prime at 2, the slope of this tangent line, oh, 3 minutes over. Okay, well, what can I say? Well, thanks for joining us. I hope it's worthwhile. It gets you thinking about the concepts you'll see next semester, practice some algebra. We did not discuss trig identities that you want to review. Namely the Pythagorean trig identities. And their cousins here, so like tangent squared. So maybe we could have taken more time with the pre-calculus stuff. So you want to, these are all pretty much the same. So these are the Pythagorean trig identities. There's power reducing identities that you'll need to know. Cosine squared has a similar one, just the conjugate. The one sine squared. So those are power reducing. Anyway, read your trig identities. I think there's, what else do we use? Oh yeah. And these half angle or double angle formulas as well. So these are the 6 essential ones. And also inverse trig functions, double angle or half angle. I don't know what they call these. But anyway, I just want to make sure that you're aware that you'll be using trig identities a lot. So you might want to use at least these 6. All right, I'll see everybody. Thank you.